It's a pleasure to introduce Christos Zacharias in Miami. I actually had a look at Christos's CV. It's always, you go to the bottom of the CVs, and he's done a lot of great things in the last couple of years, but you go to the bottom of the CV and then you see the personal interests. So there's guitar, marathons, tennis, karate, and know thyself. And that's, I guess, in conjunction to military service in Cyprus and being in the Mathematics Olympiad. But since then, a lot of work in management science, stochastic management science. So thanks a lot. Let's hear what you have to say.
Well, Yoni, thank you so very much for this very kind introduction. I really appreciate it. And I would like to express that I'm very humbled and very excited to be here today among you to present my latest research. And also I would like to take a moment to acknowledge that I was late. I was teaching, and I would really like to see the whole presentation. Peter, I'm familiar of your research. I have read your papers, the ones with Avi Mandelbaum. He was part of my PhD committee. Today, I'm going to present some discrete queuing and discrete optimization results, combinatory optimization. However, in my dissertation, also I have done some work with diffusion approximations, Brownian diffusion approximations. And I've read some of your papers, Peter. So that I would just like to acknowledge that. So I'm very excited to share with you my latest research. This paper I'm going to present today is the climax of a line of research I have been pursuing for many years now, since my PhD studies. And when I firstly came across this problem, I thought it was going to be impossible for me to ever try to even approach it. But I think over the years of gaining knowledge in this field and with the right co-authors, we managed to tackle it. And I'm very satisfied with the outcome of this research. It has been accepted recently for publication in operations research. So this is joint work with my co-authors, Nan Liu from Boston College and Mehmet Beken from Western University. And at a very high level, how does this work fit within the framework of queuing and operations research? I would say it relies both on queuing and discrete optimization. So it's discrete optimization of a system where the objective is not given by an oracle, is given by transient analysis of a queuing system. So now some motivation about this research. It is a common phenomenon for patients to show up for their appointment on time and still having to wait to see their doctor. It happened to me more times than I care to remember, and I'm guessing it might have happened to some of you as well. So why is this happening? Is it because of bad scheduling? Is it because of overbooking? Is it because of variability involved in outpatient processes? Is it because of an emergency? Probably a little bit of everything. So besides long waiting times at the doctor's office, patients also often experience difficulties to get access to an appointment in a timely manner. So according to this study presented in this slide, Americans wait on average for 18 days to get an appointment for outpatient services, and this delay depends on the specialty. So we have two timescales involved in accessing outpatient medical care. We have the indirect delay and direct delay. Indirect delay is defined as the time gap between the request for an appointment and the actual offered appointment. It's in the order of days, sometimes weeks, even months. On the other hand, direct delay is the physical wait experienced by patients once they arrive at the doctor's office. It's in the order of minutes, in extreme cases, in the order of hours. So as an academic field, subfield of operations research, in the appointment scheduling problem at a very high level, we address the question of how to manage patient arrivals in outpatient systems so that patients experience short waiting times, timely access to care, and at the same time, the system utilizes valuable resources efficiently. So we want to manage patient arrivals in two different timescales across different days in the horizon, interday scheduling, and within a workday, intraday scheduling. So what makes this problem challenging? One of the factors that make this problem challenging is its highly stochastic nature. Outpatient clinics have to deal with many sources of variability, including patient no-shows, no punctuality, emergency walk-ins, stochastic consultation times, stochastic demand for outpatient services, patient heterogeneity, preferences, seasonality, and the list goes on. Moreover, the underlying optimization problem is often computationally complex one, and it has a discrete nature. And in dynamic settings, we have the inevitable case of dimensionality. So there is an extensive literature on this topic, starting from 1950s, and this is still an active area of research. There's many ways to classify the literature based on the model, assumptions, optimization framework, and so on. So if we will look horizontally, this table, one way to classify the literature is to distinguish between static and dynamic models. In static models, we make all the decisions simultaneously by assuming that we have access to all the necessary information to make such scheduling decisions in advance at the same time. In dynamic models, we optimize the system dynamically, and we take into account the ripple effect of today's decisions to future outcomes. So now if we look at this table vertically, there is extensive literature on intraday scheduling. So in intraday scheduling, we want to optimize a single day's operations, disregarding demand variability and probably other factors. So we look at the single day, disregarding the big picture, and we address the question, how do we manage patient arrivals within a single day so that we optimize the system? To optimize the system means to utilize resources efficiently and patients, meanwhile, to experience reasonable waiting times. And as you can see in this table, this is the most crowded area of the field, static intraday scheduling. So we have also interday scheduling models in the literature. In interday scheduling, the decision is how to assign requests for appointment to future days without caring much about the specific time to arrive. So by looking at a high-level picture of the system, how congested is the system, how long patients have to wait to get an appointment, we take this kind of attributes into consideration when making a decision in what day to schedule a patient. There is some work on joint interday and intraday scheduling with static queuing models in steady state. And to the best of my knowledge, the dynamic joint interday and intraday scheduling problem had remained an open problem due to its complex structure, stochastic nature, and the case of dimensionality. It has been recognized, in fact, by other scholars in the field, not only me being here and expressing that. And the scope of this article is to address this problem, the dynamic interday and intraday scheduling problem. And our approach is to bridge together the two seemingly independent streams of literature of static intraday scheduling and dynamic interday scheduling. So we're going to build upon the theoretical results of two recent papers, both published in Management Science, and provide theoretical connections between them so that we can provide a platform to address the joint problem. So more formally, here's the research question. The scope of this research is to develop and analyze a dynamic interday and intraday scheduling model. So we would like the model to be mathematically computationally tractable. And at the same time, we would like the model to be realistic enough so that it is useful for practical implementation. And our approach is to provide connecting links between two papers from the literature, fairly recent papers. One is by Truong 2015, published in Management Science, Dynamic Interday Scheduling. And I would like to acknowledge this paper that in my subjective understanding of the field, this paper is regarded to be a breakthrough paper in interday scheduling. So for the first time, elegant dimensionality reduction results have been proven for this problem. And a recipe for an exact solution, not a heuristic solution, was provided to solve a multidimensional dynamic program. And so this is Interday scheduling, Truong 2015. And the other paper comes from static intraday scheduling, also published in Management Science. So the main contribution of this paper, Zacharias and Younes, is to prove that the static intraday problem possesses a property called multimodularity for general stochastic service times, stochastic walk-ins, and no-shows. So multimodularity is a discrete convexity property. It's a combinatorial optimization property that guarantees the success of certain optimization algorithms. So before I jump into the model and discuss our analysis, I would like to take a moment to talk a little bit about the role of convexity. So in continuous spaces, convexity is a property very well defined. It is a property that guarantees that the local mean is a global minimum. Therefore, we can identify this local minimum. If the function is smooth, we can take the first derivative, set it equal to 0. Otherwise, we can also use some gradient descent methods and find this minimum. So either analytically or with gradient descent methods. But how do we optimize a nonlinear function defined over discrete spaces? Even linear functions defined over discrete spaces sometimes is computationally very expensive, the branch and bound kind of algorithms. So how do we optimize a function defined on discrete spaces, especially nonlinear? It is crucial to identify structures that guarantee the success of some efficient optimization algorithm. So how do we define convexity in discrete spaces? How can we define this notion that a local mean is also a global mean? We cannot take derivatives. We cannot use the epsilon definition. It's a discrete space. So do we consider possible combinations of unit directions? There is various notions of discrete convexity established in the literature. I would like to talk briefly about two of them, multimodularity and L-natural convexity. So L-natural convexity was introduced by Murata, a Japanese mathematician and operations researcher. It is a property which is stronger than submodularity. And multimodularity, introduced by Hayek in 1985, is a property stronger than supermodularity. And Murata proved that these two properties are related through some linear transformation. And the properties of one can be transferred to the other by using duality arguments of that transformation. So both properties guarantee that the local minimum is a global minimum. However, the local neighborhoods look different. And this is an example of what the local neighborhoods look like. So on the left-hand side, we have the local neighborhood of some vector x under L-natural convexity. And on the right-hand side, we have what the local neighborhood looks like under the notion of multimodularity. They have some neighbors in common. They have some neighbors that are not in common. And the size of the local neighborhood for both notions of discrete convexity is exponentially large. So this is a number that increases exponentially with the size of the problem. It is manageable for small values of n, but for some large, meaningful values of n that you see in practice, it's because it explodes exponentially, it's impossible to thoroughly and exhaustively search the neighborhood. So this was my introduction and motivation. So in what follows, I'm going to firstly introduce the dynamic programming framework, and then I'm going to briefly discuss the contributions of Truong 2015 and Zacharias and Younes 2020. And finally, I'm going to present how we build upon the results of these two papers and how do we provide a solution to this practical problem. So before I proceed, are there any questions regarding my motivation and the problem? Okay, I'll proceed. So at the very high level, this is what the dynamic programming formulation looks like. The state of the system is a matrix. And this matrix represents a schedule. The rows of this matrix represent different days in the scheduling horizon. And the columns of this matrix represent different slots. So one workday is discretized into a number of slots of equal duration. So this is a high-dimensional state space, which is problematic in dynamic programs. So our best hope to solve this problem is to not solve it computationally because it cares of dimensionality. And we have a multi-dimensional state space, which is a matrix. So our best hope is to prove theoretical dimensionality reduction results or provide good heuristics based on theoretical grounds. And this is what the dynamic programming formulation looks like. So the sequencing of events. First, we observe the current state of the system, which is a schedule, a matrix. Then new demand is realized and observed. We make a decision of how to allocate this new demand to future days in the horizon. We update the schedule by adding these two matrices. And tomorrow's updated schedule is the first row of the updated matrix based on the decision we made today. Accordingly, we incur the interday and intraday costs. And finally, we update the state of the system by removing the first row and moving on to the next period. So in this Bellman equation, you can see that we penalize for having a congested system, many patients registered in the appointment book waiting to see their doctor. And we also penalize based on some function of the schedule. So this model balances the trade-off between having a congested medical facility with patients experiencing long waiting times at the doctor's office, and on the other hand, providing timely access to care. So in this model, we assume that the interday scheduling, the interday cost, is a linear indirect waiting cost for all patients, and that the intraday cost function is a function of a vector and it's assumed to be multimodular. More about this assumption later on. So next, I'm going to present and summarize the results of Truong 2015 on dynamic interday scheduling. And then Zacharias and Yunus, and finally, I'm going to present our contribution based on the results of these two papers. Without presenting the results of these two affirmation papers, it's impossible to make our contribution clear. So Truong 2015, Optimal Advanced Scheduling. In this paper, she addresses the dynamic interday scheduling problem. So upon request, we dynamically assign appointment date, but not appointment time. Therefore, the state of the system is reduced from a matrix to a vector. And the components of this vector capture the number of patients scheduled to arrive in future days in the horizon. So the sequence of events is analogous. We want it to be consistent with the assumptions of the modeling of this paper. So we observe the current state of the system, a vector, new demand is realized, and observe the scalar. The booking decision is a vector. We update the schedule accordingly. And tomorrow's updated schedule is not a vector, is a scalar, a single number. And this number tells you how many patients are scheduled to arrive tomorrow. So the value function satisfies a similar Bellman equation. The interday cost function penalizes linearly with the number of patients registered in the appointment book. And the intraday cost function is assumed to be a convex function of one variable. So I would like to take a pause here and make the connection between multimodularity of a vector function and the convexity assumption of a function of one variable. And the main contribution of this paper is the following. They demonstrated that the multi-dimensional dynamic program can be broken down into multiple versions of single-dimensional MDPs. So if we relax the constraint that our prior commitments to patients are binding, so suppose that I have an appointment book with patients waiting to be served, and new demand is realized, and I relax the constraint that I need to satisfy the prior commitments. And if we solve this new unconstrained problem, it turns out that the solution to the unconstrained problem is a refinement of the existing schedule. In other words, we can generate the solution to unconstrained problem by building up on top of the existing schedule. And this is based on the very elegant property of successive refinability. So in summary, Truong 2015 provides what I believe to be a very elegant and exact and computationally efficient solution to the dynamic interday and intraday scheduling problem via the property of successive refinability. So next, I'm going to present and summarize the results of myself and my colleague here at Miami, Talis Younes. So this paper was also published in Management Science. And in this paper, we address the static intraday scheduling problem under general stochastic service times, either discrete, continuous, or a mixture, walk-ins and no-shows. So we perform exact transient analysis of a queuing system, and we prove discrete convexity properties of the underlying optimization problem. And we demonstrate how to solve the computationally complex problem, not only effectively, but also efficiently. So in this paper, there's a queuing component, and there's also a discrete optimization component. So we unfold discrete optimization properties of some objective function, and this objective function is not given by an oracle, it's the outcome of stochastic analysis in transient state. And also objective function evaluations are involved. They are computationally not cheap, say. And we unfold discrete convexity properties, including supermodularity, directional convexity, and multimodularity. And with this visual here, I'm trying to convey that directional convexity is stronger than supermodularity, and that multimodularity is even stronger than directional convexity. So a brief definition for those who are not familiar. We say that the function defined over non-negative interior vectors is supermodular if it possesses increasing differences in different directions. Directional convexity is a property slightly stronger. So directional convexity means supermodularity and component-wise convex. To the best of my knowledge, directional convexity alone does not guarantee optimality of local optima under any definition of locality in the literature. And I found this to be very frustrating, to be honest with you, when I was researching this area. In my understanding of discrete optimization and queuing, I would have hoped that directional convexity, such a strong property, would guarantee the success of some optimization algorithm. It turns out no. Then we have multimodularity, which is a property a little bit stronger than directional convexity. So multimodularity was firstly introduced by Hayek in 1985 within the context of optimal admission control to queues. So optimal admission control to queues, appointment scheduling, they have a similar flavor in the sense that we have control over patient arrivals. So it's not surprising that the appointment scheduling problem possesses this property as well. So I would like to note that this is not the definition provided by Hayek. This is an equivalent definition that we prove in the paper, which I personally find to be more intuitive and facilitates better exposition of the results in the analysis. So Murata 2004 proves that multimodularity is a property that guarantees that a local mean is a global mean. So this is good. We have an optimality criterion. We know that once we identify a local minimum, we have a global minimum. Moreover, Murata demonstrates how to build a local neighborhood of a vector X. So we build a local neighborhood by adding an alternate sequence of positive and negative unit deviations. And the size of this local neighborhood grows exponentially fast with the dimension of the problem, which is problematic when it comes to solving large, meaningful instances of the problem. So I would like to excuse myself for 5 seconds. I had daylight earlier and the light was good. Now I need to turn on my lights.
No problem.
Is it better now?
Yes, see you well. Okay.
This is a reminder that summer is over because it gets dark so early, 7:30. So as an example, this is what the local neighborhood looks like in 3 dimensions. So of course, this local neighborhood exists in higher dimensions as well, but the human brain can only visualize and understand visually 3 dimensions or lower. So the same idea can be extended to higher dimensions. So with the green circle in the middle of this graph, we have a vector X. With the red squares, we have the neighbors of that vector X. And with purple stars, we have the rest of combinations of unit directions. And how do we get these neighbors? We need to add an alternate sequence of positive and negative unit directions. So the plus minus sign has to alternate. So we can have 1 direction, we can have 2 directions, or 3 directions. And once we generate these directions, starting with the positive, then we also add to these directions the minuses, the negatives of those. So in 3 dimensions, a vector X has 14 neighbors, and this number grows exponentially fast. So now about the queuing model and the optimization scheduling model. So in this paper, we model the workload of the outpatient clinic as a single server queue with non-homogeneous arrival process and general stochastic service times in transient state. So service times are general stochastic. It could be either discrete or continuous or a mixture. We assume that the queue is work conserving, the server is not allowed to be idle when there is workload, and that the service discipline is FIFO. Now about the time scale. Time is measured in minutes, and the length of the regular workday is denoted by capital T. So the time scale here is minutes. Time is continuous, but the workday is partitioned into a number of discrete slots of equal duration. And I would like to point out here that the number of slots is a parameter of the model, it's not something fixed. And we can play around with it, and there is a trade-off. So for example, if I set the slot duration to be equal to 15 minutes, it doesn't mean that I compromise the service times to be 15 minutes. It means that I refine the time scale of the schedule. So suppose that the average service time is 30 minutes. Do I bring in patients in integer multiples of 30 minutes, like 8, 8, 39? Or is there any benefit to allow to have a more refined schedule to bring them in every 20 minutes maybe, or every 15 minutes? Or maybe have 15 minutes, then a gap, and then another 15, and probably front load the day. So I would like to make this, to emphasize this, that the number of slots is a problem parameter that we can play with. And if we make the slots shorter, doesn't mean we compromise service and the service time. It means that we have more flexibility in our scheduling. And everything that happens after capital T is considered to be overtime workload. So given a discretization of a workday, X1 represents the number of patients assigned to the first slot, X2 represents the number of patients assigned to the second slot, and so on and so forth. And the optimization problem is to figure out what is an optimal schedule, what is an optimal non-negative integer vector that minimizes a weighted sum of systems idle time, overtime, and patients waiting time. And the main result of this paper is that the objective function is multimodular under general stochastic service times, patient no-shows, and emergency walk-ins. This is a result that makes the problem amenable to exact solution under general stochastic service times. So before this work, multimodularity had only been proved for exponential service times and deterministic. I don't need to spell out in this audience, I believe, why exponential service times have nice properties in queuing. It's because of the memoryless property. A similar argument can be expressed for the deterministic service times, that both these service times, deterministic and exponential, make the use of keeping track of a workload process not necessary. You just need to keep track of the number of customers or patients in the system. And the main challenge, in my understanding of the proofs of multimodularity in this case, was to figure out new proving techniques and arguments to prove multimodularity based on a workload process, not a queue length process. So we have these results that the objective function is multimodular under general stochastic service times. We know that the local minimum is a global minimum. Therefore, we know that in theory, the problem can be solved to exact optimality. But on the other hand, the size of the local neighborhood grows exponentially fast, which is problematic to solve meaningful instances of the problem. So the question we address is the following. Can we solve the problem in polynomial time more efficiently? So in addition to the local neighborhood growing exponentially fast, I would like to note that objective function evaluations are quite involved. It requires some computing time. So not only we have exponentially large local neighborhoods, objective function evaluations, they are not cheap. So it is problematic. We cannot solve meaningful instances of the problem. And another contribution of this study is to show that we can do indeed optimize such functions in polynomial time, not exponential time. I'm not going to go through the details of this proof, but I would like to expose the main steps so that I present to you to get an idea of what are the main methodological tools involved in this theorem. So for a multimodular function f, we know based on the work of Murata that with a linear transformation, it can be expressed as an L natural convex function. And Murata himself has done quite some work on L natural convex functions and different types of discrete convex functions. Therefore, the problem of minimizing a multimodular function over non-negative integer vectors can be translated to minimizing an L natural convex function subject to non-trivial constraints. Minimization of L natural convex function subject to non-trivial constraints can be then translated into submodular set function minimization So between steps 3 and 4, we are transitioning from minimizing functions defined over vectors to functions defined over sets, set functions. And then we proved that the constraint set of this non-trivial constraint problem with non-trivial constraints is a ring family of subsets. And we identified these jointly reducible members. And based on this, and based on the results of Schreiber, when the constraint set of constraint submodular set function minimization problem is a ring family of sets, and we know the jointly reducible members, then we can translate this problem to step number 6, unconstrained submodular set function minimization. So you can do a transformation, and so you have a problem of minimizing a set function over a ring family of sets. And if you do the proper mapping and transformation, you have an unconstrained minimization problem of submodular set function, which is known to be in polynomial time. It's known to be in polynomial time solvable before the work of Orlin, but Orlin provided the faster method from his predecessors. So finally, after I have set the platform of what we are trying to address in this paper and our intention to produce results that bring together the two seemingly independent streams of literature, I would like to present our results. So I would like to note at this point my understanding that the two streams of literature on intraday scheduling and interday scheduling have been separated. I have not seen connections between them. They have been studied, I believe, in isolation. And in this research, we provide a model that brings together these two streams of literature and will leverage the theoretical results from both streams. So Truong 2015 they address a dynamic interday scheduling problem where the intraday cost function, so the cost function that captures what happens within a workday, is a function of a scalar, the number of patients in the schedule. So in Truong 2015, the intraday cost function does not take into account the detailed intraday dynamics, how patients are scheduled to arrive, and any queuing that might happen and waiting. It is assumed to be some general convex function, which is a plausible assumption, but it's not a function of a detailed schedule. It's just a function of a scalar, convex function. In Zacharias and Younes, on the other hand, we address the static intraday problem. We ignore the interday dynamics, but an intraday schedule is affecting the objective with the detailed dynamics via a vector. So we have a vector that describes how patients are scheduled to arrive throughout the day. And the number of patients in the schedule is the outcome of unconstrained optimization. So we minimize a multimodular function over non-negative interior vectors, and the outcome is an optimal schedule. And moreover, based on that optimal schedule, you take the optimal number of patients to be scheduled. So here's the connecting link between the two papers. The connecting link is the number of patients in an intraday schedule. So we propose two scheduling paradigms under which the intraday cost function will be a function of a scalar, similar to Truong. However, this intraday cost function is not some general convex function. It will be the outcome of work. It will be the outcome of constrained optimization. So this scalar appears in the right-hand side of an equality constraint of an optimization problem. So it's not given by an oracle, this function of a scalar. Can we compute such function efficiently in a meaningful way? Is such function convex? Does it satisfy the assumptions of Truong 2015 so that we can apply the concept of successive refinability? So in what follows, I'm going to introduce two scheduling paradigms. The first one is the re-optimized intraday scheduling. So in re-optimized intraday scheduling, we consider the original problem where the state of the system is a matrix. However, we relax one constraint. We allow re-optimization of the patients scheduled to arrive tomorrow. So the scheduler, when he has the full schedule for tomorrow, say at midnight, can re-optimize the static intraday schedule for tomorrow and call the patients, and the patients will show up in those re-optimized times. This is unrealistic. It doesn't happen. This is idealistic, but consider for now that we're allowed to do that. So therefore now, due to the fact that we can re-optimize tomorrow's schedule, under the constraint that the number of patients in the schedule is fixed, so the state of the system reduces from a matrix to a vector. So in the bottom left corner, we have this constraint optimization problem. So we allow rearrangement of the arrival times of patients scheduled to arrive tomorrow, but we're not going to offer them a different day. We're just going to offer them within the same day, just a different time slot, last minute. Therefore, the number of patients in the schedule remains a constraint. It is the right-hand side of a constraint minimization problem that involves a multimodular function. In Zacharias and Yunus, we demonstrate that we can solve this problem effectively and efficiently without the constraint. Does the constraint make it more difficult? And the answer is no. So one of the main results of this paper is that we proved that the constraint problem you see in the box, it is solvable in polynomial time. And moreover, another important result is that the underlying function is convex. So it's a convex function of one variable, and this variable appears on the right-hand side of an equality constraint. And therefore, we can leverage this convexity to apply the successive refinability property of Truong 2015, and therefore solve the problem under this relaxation effectively and efficiently. So this scheduling paradigm, it's a relaxation of the problem, of the original problem, of the task at hand. It is practically not very reasonable. You cannot re-optimize at the last minute patients' arrival times. However, it is analytically tractable and provides a lower bound to our objective function, our value function. Now consider a different scheduling paradigm with the name Sequentially Refinable Intra-day Scheduling. So we say that the sequence of vectors is sequentially refinable if this sequence is increasing. And less than or equal is component-wise. So every single component has to be less than or equal to the successor in this sequence. And also, the first member of the sequence has one patient, the second member in the sequence has two patients, and so on and so forth. So under this scheduling paradigm, with sequentially refinable intraday schedules, any changes in the schedule are made by new requests, which is exactly what we need in the practice of appointment scheduling. You want to build on top of the existing schedule. So we construct such a sequence of schedules centered around the solution to the unconstrained problem. So first, we disregard the interday dynamics, demand variability. We look at the single day, and we ask the question, what is the optimal schedule for a single day today, disregarding tomorrow and the ripple effect of today's decisions. So firstly, we solve this problem. And then by moving to both directions, by adding or removing one patient, we build sequentially such sequence by re-optimizing the system. Therefore, the intraday cost function now can be expressed as a function of a scalar, the number of patients in the schedule. So if you know the number of patients in the schedule, you can do the mapping to the corresponding vector. And therefore, you don't need to keep track of a whole vector. You can reduce the state space from a matrix to a vector. And it turns out that such scheduling paradigm results in an intraday cost function of a scalar, which is convex, and we can compute such function efficiently. So we can use this convexity property to apply successive refinability and therefore provide a solution to the corresponding dynamic program, which is computationally feasible and tractable. So the first scheduling paradigm I introduced is a relaxation of the original problem. And this scheduling paradigm is a special case or additional constraint. So this one can be regarded as a heuristic solution because it is feasible to the original problem. So we have a heuristic solution based on theory, and we have a relaxation. Therefore, we managed to sandwich the actual optima. So we have a tractable heuristic. It's a heuristic based on theoretical grounds, and also the value function is tractable as well. And we have also a tractable infeasible solution, the relaxation, where we're allowed to re-optimize last minute. So our value function is somewhere in the middle. And also I would like to point out here in this slide at bottom right that the two intraday cost functions, both of them functions of a scalar. So in the blue line is the case where we can re-optimize at the last minute by keeping the number of patients fixed. So for example, given 10 patients, what is the best way to schedule them? Blue line gives the associated cost. The red line gives the cost associated with having sequentially refinable schedules. By construction, both functions have the same minimizer. Not only they have the same minimizer, but their value at that minimizer is the same. So because the sequentially refinable schedules are constructed around the solution to the unconstrained problem. And also, as shown in this figure, we know from theory that both functions are convex, and they're also very close to one another. They're not far away from each other. So we have sandwiched the objective function between two tractable dynamic programs. So one of the dynamic programs provides a lower bound through the corresponding value function. But on the other hand, the optimized intraday schedules are infeasible. I mean, they are not practical for actual operations. On the other hand, SRIS, sequentially refinable intraday scheduling, provides an upper bound through its corresponding value function, and it is tractable. So it is also a heuristic solution. So because it has a more constrained solution space, it is a heuristic solution and it is feasible for the original problem. And based on these two scheduling paradigms, we can provide an upper bound on the optimality gap. So in the last couple of minutes left, I would like to present quickly computational implementations of our methods. So we have implemented computationally our scheduling paradigms. Our model input, I would say, takes 15 different inputs, cost parameters, distributions. There's many inputs in this model. And we we implemented computationally our optimizations for a wide range of parameters in the orders of many thousands. And the results I'm going to present to you, which is a small sample of the whole computational analysis, are consistent throughout the whole parameter space. So first, we know that we have a theoretical upper bound on the optimality gap because we have a lower bound, an upper bound to the value function. We can use these two to provide an upper bound to the percentage optimality gap. And the first thing that we wanted to know, to find out, what's this percentage optimality gap? So here I'm presenting a sample of our analysis for different cost coefficients for the interday cost that captures the relative importance between waiting too many days to get an appointment and having a congested clinic, and the arrival rate, which is the demand rate for appointments. And it turns out that the percentage optimality gap is 1% or below across all the states of the system and across the whole parameter space, which is strikingly a pleasant result that based on the construction of the two scheduling paradigms, we managed to provide a heuristic solution with a computationally tractable performance guarantee. We don't know analytically what is this bound. Is it 1%? Is it 2%? Is it 3%? We cannot generalize this result to a specific number. What is the percentage optimality gap? However, by implementing computational methods, we have demonstrated that for a wide range of parameters, it's always consistently less than 1%. So this could be attributed to the commonalities between the two scheduling paradigms. They do have the same minimizer by construction. They both have been shown to be convex. So imagine a system where demand, there is no variability in demand. Demand is deterministic. And we can every day deterministically have the same minimizer. So that would give an exact optimal solution. But in reality, because of demand variability and probably other factors, we don't always have the same optimal number of patients. And based on the small differences between the two functions, we have this small difference in the optimality gap. So in the next experiment, we wanted to investigate what is the difference in the optimal controls between the two scheduling paradigms as captured by the allocation function. So remember Truong 2015? She solved a multi-dimensional dynamic program by solving multiple versions of a single dimensional program. So you can break down the multi-dimensional to multiple versions of single dynamic programs, which can be solved fast. So the state of the system has been reduced through dimensional reduction results to a scalar from a vector. In our analysis, in our dimensionality reduction results for the two scheduling paradigms, we reduce a matrix to a vector as consequently to a scalar because of convexity. So now this optimal control of a scalar, the number of patients in the whole system, we would like to see how it differs for the two scheduling paradigms. And here we have a snapshot of our analysis for different states of the system and different parameters of interest. So for the majority of the state and parameter space, these functions of one variable, control functions of one variable, are identical, as demonstrated by the white space in this graph. And their absolute difference is equal to 1 for all the instances that we solve of the problem. Sometimes one of them is above the other, but always the difference is equal to 1, which we found to be very interesting and noteworthy. And finally, in the last experiment, I would like to show you what an optimal allocation policy looks like. It possesses some properties that I believe are useful for practical implementation. So in this heat map, blue is cold, small values, red is hot, large values. So we see how many patients we schedule to arrive tomorrow based on the state of the system. So for the optimal unconstrained problem, we want 18 patients every day. So when the state of the system is less than 18, every patient gets the same day appointment. But due to demand variability and probably other factors, probably mismatch between supply and demand, for higher values of the state of the system, we increase the number of patients we squeeze to arrive tomorrow, but in a concave manner. So, and this concave increase captures exactly the trade-off that we want. That on the one hand, you don't want to have patients waiting for many days to get an appointment, but on the other hand, you don't want to have a congested medical facility. And with that, I would like to conclude and summarize that in this paper, we address the dynamic interday and intraday scheduling problem, a problem that has been deemed to be a challenging, open direction of research. We build a model to address this problem by leveraging the results of two recent papers in the literature, one from dynamic interday scheduling and one from static intraday scheduling. So we proved novel theoretical results regarding multimodular function minimization. We leverage these results to do the proper connecting links between the two papers and to provide a heuristic solution based on theoretical grounds, which has a theoretical performance guarantee. An extensive computational implementations of our method demonstrate that the optimality gap is consistently less than 1%. And with that, I would like to conclude. Thank you and welcome any questions I have in the next 1 or 2 minutes.